So in this video, I'm going to explain the buoyancy force. So when objects are placed under water or any liquid, there's a buoyancy force that'll push the object up. We'll call this F(B) for buoyancy. There is a force of gravity acting down on the object, but when the object is placed underwater or under liquid, there's a buoyancy force. This buoyancy force, this buoyancy force can be evaluated by using Archimedes Principle. And Archimedes Principle basically states that the buoyancy force equal to the weight, of the displaced liquid. That's to say that whatever the object is placed, this object has a volume V. So whatever liquid that is displaced, because of this volume, the weight of that liquid is the buoyancy force. So that is to say that if the liquid has a density rho, I'll put LIQ, and the volume of the object is V, then the buoyancy force is basically the mass of the liquid that would have occupied this volume. So the mass of the liquid I'll put LIQ, times G, gravitational acceleration, is the buoyancy force, FB. Now this mass, of the liquid is divided by the volume of the liquid, or the volume of the object, times the volume of the liquid is G, and this is density. So sometimes a lot of people write this in terms of the density of the liquid times the mass of the volume of the displaced volume. So I'll say this is the volume, just call it V for short, times the gravitational acceleration is the buoyancy force. This is called Archimedes Principle. So let me give you an example of this with water. So here's an example. Assume that we have water, we have a box, and let's assume the volume of the box is just 1 cubic meter, and the density of water is known to be 1,000 kilograms per cubic meter. Fresh water without any minerals in it, just distilled water, is 1,000 kilograms per cubic meter approximately. And so the buoyancy force, so this object feels the force of gravity pulling down, but the buoyancy force, FB, is given by the density of the liquid, water in this case, times the volume of the liquid, times G. In this case, it happens to be 1,000 kilograms per cubic meter, times a volume of 1 cubic meter, times acceleration, and I'll round this off to 10 meters per second squared at the Earth's surface. So the cubic meters drops, the kilograms meters per second squared is in newtons, so this is 10,000 newtons. So there's a force of 10,000 newtons pushing up. The buoyancy force is pushing straight up, pushing the object out of the liquid. So, and there's a force of gravity pulling down. So this is called the buoyancy force, and it's called Archimedes Principle. let's take an example of this with assume that we have a stick. And let's assume that this stick, right, is placed into a cylinder of water. So here's our cylinder, here's our water, here's our stick. And it's got a cross-sectional area A. And let's assume that the stick has a length of L that's underwater, lowercase l. And the question is, so it's got a cross-sectional area A. It might be a square, it might be a rectangle, or it might be a circle, but it's a piece of stick. It's got a uniform cross-sectional area. Its length L. And we're asked, right, to find the density. Oops. And this is water, so H2O. And the density find the density of the stick. So find I'll also assume that the full length of the stick is L. So we know the full length, we know the L that's below the water, we know the full length of the stick, and so our problem is to find the density of the stick. I'll call rho to be the density of the stick. Ooh. And I'll call rho H2O, let's call it W, actually water. This is the density of water. So again, we'd like to find the density of the stick, assuming that the stick has a cross-sectional area A, it's got a full length L. The lowercase l is the amount of the stick that's below the water. It happens to be in a cylinder, and so we're going to use Archimedes Principle to find the forces acting on the stick first. So let's do a free body diagram. Here's our free body diagram. So our free body diagram says that there is a buoyancy force, Fb, and then there's a force of gravity acting down on the object. So there's only two forces acting on this object, and so whenever this object is floating, the stick is floating in the water, so all we know is that the sum of all forces is equal to the buoyancy force, which is acting up, plus the force of gravity, which is acting down. So the sum of all forces, the stick is at equilibrium, so I'm going to put this at 0. So sum of all forces are not causing the stick to accelerate, so it's 0. The buoyancy force, and I'm going to use only as up is positive. So I know that the displaced volume, right, of the stick underwater is given by, well, the density of the liquid is H2O. So let's put that in, W. The volume that's being displaced, right, is area times lowercase l. So this is the mass. We're expecting g to be the gravitational acceleration at the Earth's surface. So this is the force that's pulling up, minus the force that's pulling down, and that's really mass times gravity. But the mass of the object, right, is given by the density of the object, which is rho, times the volume, which is area times length, times, this is the mass, times g. And I'm sorry, it's not lowercase l, it's capital L. So this is the total mass of the whole stick. So this is the mass that's pulling down. Notice that we can drop the area, the G drops, and we're left with 0 is equal to the density of water times the length that's below the water minus the density of the object times the full length of the stick. And so rearranging this, you can see that the length over L is equal to, move it to the one side, divide by L, and so you get rho times rho density. Now we had to find rho, so rho is equal to the density of water times L over L. So this means that if I know the amount of the stick that's below the water to the full length of the stick, multiplied by the density of the water, right, we'd be able to find the density of the stick. Since L is smaller than L, we expect this density to be lighter. So the wood will be lighter because that's why it's floating. So let's take another example. So I'd like to find the weight of 10 kilograms of a metal which has a density of rho. Let's make it as 8,200 kilograms per cubic meter under water. So find the weight of 10 kilograms of a metal which has a density of 8,200 kilograms per cubic meter underwater. So the idea is that here's our liquid, here is our mass of object, it's got a certain volume V, and I put it on a scale underwater. So if I had a scale, so here's our little measurement. So here's our mass of the object. So I put this mass on this, and so I'd like to know what the weight of this object is. If we just had to find the weight outside air, this would be just 10 kilograms times G, which is about 10 meters per second squared. So we're expecting a measurement of 100 newtons. But it's underwater now. So we have to use the density of the object and use the buoyancy displacement. We have that it weighs 10 kilograms, so we know its volume. So let's ask ourselves, we do a free body diagram again. So here's our free body diagram. So here is the buoyancy force acting up on the object, and then there's a force of gravity pulling down. And so we could write again sigma F. Now, there is a normal force, right, that the scale measures, so we have to put that in. So the normal force is N, and it's pulling up. So all I know is that the sum of the normal force pushing up, the buoyancy force, and the force of gravity is equal to 0. So the sum of all forces is equal to 0, but that's equal to the buoyancy force plus the normal force plus the force of gravity. I gotta put little arrows everywhere, so that, these are arrows. So let me write this code over to here. Derivation is going to be over here. So 0, I'll use up as positive. The buoyancy force is basically the volume of displaced liquid. I'll use rho W to mean density of water. Which in this case happens to be 1,000 kilograms per cubic meter. Of course, salt water is a little more dense than that, but let's not worry about little things like that. It's like off by less than 1%. So the density of water, and so what's the buoyancy force? So your buoyancy force is basically the volume times the density of the water. So I'll just put this as, it is the density of the water times the volume of the object, and the normal force, that's what we're trying to calculate, the normal force is acting up, so that's plus m, minus the mass of the object, m, and pulling down, mg. So we can say that the normal force then is equal to the density of water times the volume of the object, mg, minus times the volume. We're told the mass of the object, so I know this, I know g, but I don't know, well, I know what the density is, but I don't know what the volume of the object is, but we can calculate this by, so we know that density of an object is mass over volume, so mass divisible by the density of the object gives me the volume. So I can rewrite this in terms of saying that this is really, oh, I forgot the g here, sorry. So here is our g. So that would mean that this would be, I can factor out the mass, both sides, so it's g minus the density of the water. Oh, actually I can factor out g too, so sorry. I'm thinking today. 1 minus rho W, it's the density of water over the density of the object. So in this case it happens to be 10 kilograms. And I'll round g to 10 meters per second squared, times 1 minus, the density of water is 1,000 kilograms per cubic meter, all over the density of the metal object, which happens to be 8,200 kilograms per meter cubed. So out comes the calculator, and we'll get our answer as something with newtons. Anyway, this is an example of using the buoyancy force to do calculations. Okay.